Alright, so I'm going to go to 7.5 now, okay? Alright, so 7.5, we're going to talk about strategy for integration. In chapter 7, we learn about different strategy, and also in 110A, we learn about u-sub, right? Okay, so we're going to put all this thing together, and then we're going to summarize, okay? So when we look at an integral, we think about what we can use to integrate that, okay? So first of all, we have some basic formula that you can maybe if you can remember them, that will come handy. Okay. So I have 15 formula over here. Okay. So when you have time, so I think most of you already know them. Okay. Just the last couple of them, maybe the number 13 to 16, you probably don't remember that well, but you can just take a look at them. Okay. Okay, so those are the basic formula that you can remember. Okay, so when you have those functions that's in one of this form, then you can just go ahead and use the formula. Okay. Now, what happens if the function that you are integrating is not of one of this? Okay, then we have a 4-step strategy for integration. Okay. Step 1 is to simplify the integram if possible. Okay, for example, this one over here. Okay, so we can use algebra to simplify it. Okay, so what should I do over here? Any suggestion? So we can multiply out, right? So we can distribute. Okay, so distribute over here. That is going to be square root of x plus x. Now you can just integrate this term by term, right? Put that in a power form. This is x to the 1/2 power, okay? And then integrate this term by term. Now, what about this one here? This one over here, you can try to simplify this by expanding this perfect square over here. To expand this perfect square here, what do we get? We get the square of sine x, right? And then plus what? 2 sine x cosine x. And then at the end, it is going to be the square of cosine x. Okay. Now by doing this, we can simplify it. Okay. So we can use some trig identity to simplify this. Okay. So we notice that sine square x plus cosine square x, that's equal to 1. So you have a 1 over here. And for this part here, we can use a double angle formula. And what does this become? That is sine of 2x, right? Okay. Now you can integrate this turn by turn, right? So, okay. Okay, so that was the first step. You simplify the integram if possible, okay? The second step over here is the easier method is the u-sub, okay? So we try to look for an obvious u-substitution, okay? So when you choose a u, you try to let u to be a function in this integram, okay, whose differential also occur, okay? For example, over here, if I let u to be x squared minus 1, okay, then what happened over here, it is x squared minus 1. Then du is going to be 2x dx. And this x dx over here, okay, it's going to match with this x dx over here. So we make the right choice over here to let u equal to this, because du has this expression here that match with this over here, okay? Now notice that for this one over here, the function that we integrate over here is actually a rational function. It's a polynomial divided by polynomial. So we could use partial fraction decomposition. We can decompose it, right, using partial fraction. However, in this case, the u-substitution is actually simpler. So if that u-substitution work, then we're going to use it instead of the PFD, which is partial fraction decomposition. Now, what happens if step 1 and 2 fail? When I was in the classroom, students would always say, well, go on to step 3, right? Yeah. So if step 1 and 2 fail, we certainly go to step 3, okay? So we're going to look at the function that we integrated, okay, which is called the integram, okay? We look at that and see what is that form, okay? What form is that, okay? So let me give you some example. Okay, so we're going to put them in different category according to the form over here. For example, the first, if that is a trig function, okay, what do you mean trig function? Okay, if a trig function of this form, like sine to some power and then times cosine to some power of x over here, where m or n here is odd. Okay, let me see you guys remember. So we're going to use this identity, sine square plus cosine square equal to 1. Okay, so the idea over here is we try to save one sine x or cosine x over here so that the remaining power of sine x or cosine x is even. Okay, now over here we have this power for sine over here is odd. Tell me, what should I save? Anyone?
We should save one of the signs.
Yes, we should say one sine x. Okay, so we're going to say one sine x with dx. Okay, that way the remaining power for sine over here will become even, right? So what happened to this sine x dx? It become d of what?
Cosine.
Well, on cosine, you got cosine, however, using the fixed sign, right? So the derivative cosine x is negative sine x. So we need to put a negative sign over here, right? Okay. So let's put this side here a little bit more obvious. So negative d cosine x. Okay. All right. So, okay. Now what happens if this exponent for cosine x here is odd? So what should I do? Save, right? Remember save. So you would say that now in order to make the exponent for cosine x here to be, the remaining power here to be even, we're going to save one cosine x over here. Okay, so we save one cosine x over here with dx. And that is going to, now the remaining power for cosine x here will be even. Okay, so cosine x dx become d of what?
Sine.
Yeah, d of sine x. Okay, d of sine x over here. Okay. Now, what happens if both exponent on sine x and cosine x here are odd? Okay, I remember one student asked about this, right? So which one to save, right? Can you guys tell me which one to save? Yeah, you can save either one, okay? So you have a choice, okay? This is a free country. So you're going to save either, okay? So we're going to save either sine x with dx or cosine x with dx, okay? So either one will work, okay? The answer will be equivalent, okay? All right, so now what happens when the exponent for on both of them are even? Do you guys remember what's the strategy? So what happens when the exponent on both of them are even? So what's the strategy? What happens when both exponents are even?
Eric is saying that you use the half angle formula.
Yes, use half angle formula, okay? So we're going to use the half angle formula. Okay, well, what happens when the function that you integrate is of this form, tangent x times secant x, where the exponent on m and n here are of these two cases, okay, right here. So for the function, when the function that we integrate is of this form, we know two cases, okay? So one of the case over here is when the exponent on the secant over here is even and greater equal to, okay? The other one is when the exponent on tangent over here is odd, okay? So we think about this identity, okay? 1 plus tangent square equals secant square. Okay, again, we use the same method, right? So when the exponent on secant over here is even and greater equal to, do you remember what do we save?
Secant square.
Yeah, we save secant square, right? So we save a secant square x with dx. And that way, the remaining power for secant here will still be even, or there's no secant. Okay, so the reason we want to save secant square here is secant square x dx become d of what? Which function when you differentiate give you secant square?
Tangent.
Tangent of x, right? Wrong place. Okay, tangent x. Okay. Okay. All right. So what happens when the exponent for tangent over here is odd? So, and yeah, what should we do? We want to save, right? To save it so that it will become even. Okay. So we're going to save one tangent x. Okay. So we're going to save one tangent x over here. But just saving tangent x is not enough, okay? Because you need to save a friend with tangent x, okay? Now, tangent x and secant x go hand in hand. So we save a secant x together with tangent x over here. Sometimes, even though there's no secant x over here, you can still save a secant x, but then later on you divide by secant x, okay? So what happened to secant x tangent x dx? This is which function when you differentiate give you secant x tangent x?
Is it secant x?
Yes. So that will be secant x, right? Okay. So that's why you want to save this together so they'll become this. Okay. Now, this one here might be a little bit new to you guys, okay? But I'm not going to test you guys. If you have cotangent to some power, cosecant to some power, you're going to use this trig identity here. The one that you save over here is kind of similar to this example over here, the one that we talk about, this case over here, okay? You do that, okay? Now, this is the trick that I told you to remember the duality for secant and tangent, okay? All right. Now, do you guys have a question? Remember, it's going to be on the test next week. Okay. All of this.
What section did we learn about saving? I'm looking through my notes and I can't remember.
Is this called? Okay. What section is this? Section 7.2.
Okay, thank you.
It's right here. Section 7.2. Yeah, I know that after a while you kind of don't remember, right? So that's why we put it here to summarize it, okay, and put them all together. Okay. So it's going to be you're going to be tested on this, okay? All right. So what happens when the function that we integrate, it is a rational function, which is a polynomial divided by a polynomial, and providing the denominator does not equal 0, okay? I'm going to ask you, what happens when the degree of the polynomial on top is greater than or equal to the degree of the polynomial down here? What do we do first? I think we talked about this on Tuesday. So what do we do first?
You said if the top one is bigger than the bottom one?
Mm-hmm. What happens when the degree up here is greater than or equal to the degree down here? What's the first step?
Long division.
Mm-hmm. Use long division, right? Okay. So we're gonna use long division first. Okay. And then after that, the remainder over divisor part, you're gonna use the partial fraction decomposition, PFD. Okay, it's not PDF. Okay, it's PFD. Okay, PFD stands for partial fraction decomposition. So it's called PFD. Okay, which is in section 7.4. So we just talked about that last time. Do you guys remember? Okay. Now, what happens when the function over here is in the form of x to some power times a transcendental function, such as, okay, what do you mean a transcendental function? Okay, it's not something that relate to a dentist. Okay, it's not related to the dental office. Okay, transcendental function over here is actually, for example, those are like trig, okay, exponential, log function. Those are called transcendental function. Okay. Now, for example, here, x to some power, okay, times a trig function, exponential function, log function, inverse trig function. The way that the strategy that we deal with it is use integration by part, okay? When we use integration by part over here, we're going to choose the u over here according to this principle, okay? The V8, okay? V, you know, okay, LID over here is like a last name for kind of like a Chinese last name, Li, right? ATE is past tense for it. Okay, so try to think about V8. Okay. Okay, so the order here is first you will, if you have log function inside, okay, you let u to be the log function first. Well, if you don't have log function, you let u to be inverse trig function. And after that, you would choose like a, if you don't have that, then you choose u to be algebraic function, okay? And then after that, trig function, exponential function at the end, okay? So go by this order when you choose u. So V8, okay? So that's the trick. Now, for example, this function that we integrate here, it is x times inverse tangent of x. X here is an algebraic function. Inverse tangent here is an inverse trig function, okay? So this is A, this is I, right? I before A. So we let this u over here to be this inverse trig function, which is inverse tangent of x. Do you guys get it?
Yeah.
Okay, right. I wonder what happened to the rest of the class. I think I'm not going to post a note, the complete note, okay? If you guys do this. Okay, all right. So over here, what happens if the function that we integrate is of this form, okay? So if it in the form like either there's a square root of a squared minus x squared plus a squared, or square root of x squared minus a squared like this, okay? So do you guys remember what strategy that we use?
Just the trig sub.
Yeah, the trig sub, okay? We're going to use the trig sub, okay, 7.3, okay? So remember this one over here, remind you of this identity, right? So the a squared here corresponds to 1 here, the x squared corresponds to this over here. You think about, so think about this identity. Okay, try to match the number here, match the x with that. Okay, you want this inside to be a perfect square. So then when you take square root, then you can cancel out the square root, and the square will cancel out, right? So you want to get a perfect square like that. So do you remember what do you let x equal to over here? Looking at this identity?
A sine x.
Yes, so we're going to let x equal to this a, and then sine x over here. No, not sine x, sine theta. Okay, a sine theta. Okay, and if you do the algebra, and then that is going to become, what does it become? If I do this trick over here, this part here become what? That is going to become a cosine theta, right? Okay, this cosine theta over here. A cosine theta, right there. Okay. Now, what about this one? So remember this identity. See, the x squared corresponds to that, a squared corresponds to 1. So think about this identity. So what do you let x equal to? A tangent theta, right? Okay. A tangent theta over here. And this is going to become what? Now at the end, this square root over here is going to become
A secant theta.
a secant theta. You got it. Okay, thank you. A secant theta. Okay. All right. Now the next one. Okay, this, okay. So you think about this identity over here. So let x equal to what? A
A secant theta?
Hold on. Sorry, I moved too fast. Okay. So over here, so this, this remind you of this identity. Why? You think about this x squared over here. You think about what square over here. Subtract this a squared here correspond to 1 over here, and equal to what square? And that is going to remind you of secant square minus 1 equal tangent square theta, right? So see the x squared here corresponding to this. So when you choose the trig sub right here, you net x here to be a secant theta. Okay, so a secant theta over here, a secant theta over here. Now by doing this, this square root over here is going to become what?
A tangent theta.
A tangent theta, right? Get this one, a tangent theta. Okay, all right. So that was a trig sub, right? So remember that. You're going to be tested on this, okay? Okay. Okay, at the end, now notice that by doing this, you're going to change the integral to be an integral with respect to theta, and then you find the antideuty. But then at the end, we want to return back to x, right? Because the function we integrate was in terms of x. So how can we change from theta back to x? We use this y triangle, right? So we use the y triangle. Whatever trig sub that you have over here. For example, here, secant theta will be x over a, and then you label this angle here theta, okay? And then secant theta x over a, then you have this hypotenuse over adjacent here. This is going to be x, and this will be a, okay? Okay, and then you get the remaining side here using the Pythagorean theorem, right? Okay, so that was the trick. Okay, now what about this one here? If the function that you integrate is of this form, we're going to rationalize it. Okay, so use u equal to this. We can also let u equal to this to rationalize it. So it become rational. Okay, this I'm not going to test you on this. Okay, that is not going to be tested. Now, if step 3 doesn't work, then we're going to try it again, right? So obviously, we have to try it again. Basically, only 2 methods, okay? Substitution and parts, okay? So you can try substitution and you can try part again, okay? And notice that integration by part also work for when this integrand over here is inverse trig function or the inverse of exponential. Okay, remember Ln of x is the inverse of e to the x. Okay, so then you can try that. Okay. Now, and sometimes you want to manipulate the integrand. Okay, for example, like if you try to integrate this, you can try to times 1 plus cosine x up and down. By doing this, the denominator here, 1 minus cosine square x, it's going to become sine square x. And then after that, you can separate this into 2 parts. For this part over here, 1 over sine, it is cosecant. So this is cosecant square. And we know antideuty cosecant square is negative cotangent square. So that will take care of it. And then for this part over here, we're going to use something, we can use u-sub, okay? So we can let u equal to sine of x, because sine of x, the derivative will have cosine x dx. We have cosine x, right? So we can use u-sub over here for this part. Or you can think about the save method. We actually save 1 cosine x together with dx. Notice the exponent for cosine x over here, it is odd, okay? So we're going to save 1 cosine x with dx right here, okay? And then that will become d cosine, that's going to become d sine x, and then let u to be sine x, okay? Notice that antideuted this, you can write this into u to the negative 2nd power, and then you find this antideuty over here, and finally return back to x, right? Okay, Okay. I'm not going to test on those. Okay. Now, if that doesn't work, then you can also relate to some problem that you have done previously, right? For example, if you have find the antiderivative of secant cube, okay, so that was a formula for secant cube. Then if you try to integrate this, you can make use of this result, okay? So we can express tangent square as secant square x minus 1, and then you distribute over here. Then secant square x times secant x, you get the secant qx, and then minus 1 times secant x over here. And the derivative, and the antiderivative for secant x is ln of absolute value of secant x plus tangent x. And then at the end, plus a constant. This part over here, you can make use of this result that we already got, okay? Now, sometimes any question? Sometimes you have to use several methods, okay? So what are those methods we learned so far? So we have u-sub, right? 7.1, we have u-sub. No, u-sub is 110A, okay? U-sub was 110A. So u-sub over here, it is in 110A, but we also did a review, okay? And by part, okay, or separate them, okay? This is 7.1. And then we did trig integral, which is sine times cosine, tangent times secant, etc. This is, I think, 7.2. Okay, so this is 7.2. And then we did trig sub. Trig sub was 7.3. Okay. And then partial fraction decomposition, PFD. Okay, that was 7.4. Okay. Right here. Okay. Okay. Now, so those are the strategy that you find the integral, okay? So now I'm going to ask you guys, see if you can do it, okay? So we're going to, you guys can tell me what's the first method of attack, okay? So what is the first? Okay, take a look at this function that we integrate. What's the first method of attack? It's one of the methods.
Could we say it's the equivalent of tan cubed x times secant cubed x?
Yeah, you got it. Okay, good job. Okay, nice. Okay, so this is equivalent to this tangent x to the third power, right? Okay, and then times secant x to the third power here. Okay, so that's in the form of trig integral, right? Tangent times secant, okay? So for tangent times secant, we know two cases, right? One case is when exponent for secant here is even and greater equal to, which is in this case, it is not, okay? It is not even right here. Another case is when the exponent for tangent over here is odd, okay? So in this case, we're going to, okay, remember this is odd. So we're going to do the save method, right? So what I'm going to save over here,
You can save one of the
yeah, so we save one of the tangent x, okay? So I'm going to save one tangent x together with the dx, okay? But saving this is not enough because we want this to become d of something, right? So what would that be?
Oh, we can save another secant and make it d secant x.
Yes. So we save another secant together with that, right? We need to save a friend. So that's one way to deal with it, right? Another way to deal with it here is to, now because we know every case for sine times cosine, maybe we can express this in terms of sine times cosine. Okay, change it into that form. Okay, now in this case, for example, in this case over here, this is going to be tangent is sine over cosine. Okay, like this. This is to the third power, right? Okay, and then here cosine to the third power. Now, if I express tangent here as sine over cosine, I was able to rewrite this function in this form, and this one over here is under this category, sine times cosine, and that might work. Okay, so sometimes you can try to change them so that it's going to be in terms of sine and cosine. Okay, all right, question? Okay, and then after that, you can do the save method again, right? Okay, either save this. Okay, okay, now what about this one here? What's the first step, first method of attack? Which method we use?
U-sub?
Use up. Yes, you got it. Okay, so gonna use u-sub. Okay, so we're gonna let this to be u-sub. Right, good job. Okay, now what about this one here? What's the first method? By part, right? Yeah, by part. Because looking at this, this is in the form of t to some power. So you use this by part over here, okay? So when you choose the u over here according to Liate, L-I-A-T-E, okay, like this, okay. Now, which one you want that u to be over here in this integral? Which one you want that u here to be?
E.
Equal to t. Yes, we got it. Okay. So this one over here, it is algebraic, right? So algebraic function. Okay. And then this one over here, it is exponential, right? Okay. So remember L-I-A-T-E. Okay. So we have algebraic before exponential. Okay. So this one over here before this one. So we let u to be this. Okay. So we want this to be, so we let u to be this. And then the remaining part over here, this part over here, we let that to be dv. Okay, so we choose u this way. Okay, right. What about this one over here? They have the same degree. What's the first thing to do?
Long division.
Yes, long division. Okay, okay. So same degree over here. So we're going to use long division first. Okay, and then we can write this as a quotient plus remainder of a divisor. This part here will be this polynomial, so we can integrate them turn by turn. This part here, remainder of a divisor, we're going to use partial fraction decomposition, PFD. Okay. Okay. Now number 5. What do you think? What method to use to integrate? Just tell me. Just indicate what's the method.
U-sub.
Yes, you got it. Okay. So it is u-sub. Okay. So we're going to let u to over here to be Ln of x. Okay. So what will be du? Du is what? 1 over x dx, right? And you see this 1 over x.
1 over x.
Okay. I can hear you now. Okay. So 1 over x dx over here. This is going to match with this one over here, right? So u-sub, okay? Good job. Okay. Now in the quiz, you're going to be asked like this. What's the first method? And then you will say u-sub, okay? All right. This one over here, you can try to manipulate this by multiply by 1 minus x up and down. By doing that, you're going to, okay. But I'm not going to test you on something like this, okay? Okay, by doing this, okay, I'm not going to talk about that one. Okay, what about number 7 over here? What do you think will be the first method of attack? By part, right? Did you say by part? Okay, yes, it is by part, okay? So over here, you have x to some power times a transcendental function. So we use by part, okay? So by part, okay? And you're going to choose the u over here according to the 8, right? Okay, go down this way. So which one we want it to be u over here?
The x square, because it's algebraic, which is above the trigonometry, the trig functions. So we choose the x square, right?
Almost, but be careful with this, okay? This inverse, this is actually inverse trig, okay? This is inverse trig function. Remember, inverse trig, okay? So what you have over here, you have this this one over here. This, it is inverse trig. This is the I over here, right? It's inverse trig. And this one over here, it is what? Algebraic, right? So algebra over here, which is this algebra. Then you have this x squared over here, okay? So you have this one and this one. So which one you going to let you to be then?
I'm going to use inverse tangent.
Yeah, inverse trig before algebra, okay? So this is not trig. If it's just tangent x, then you do that, right? Wait, not R-A-T-E. You can do trig, yeah. So inverse trig before algebra. So this one here, you want this to be u, okay? So you want u over here to be inverse tangent of x. Then du over here will be what? What's the derivative of inverse tangent?
1 over x squared plus 1.
1 over 1 plus x squared. Yes, you got it. Okay, and then dx. Okay. By doing this, and then you're going to let the dv over here to be the other one, right? Okay, so the rest over here will be dv. Okay, so dv over here, so dv over here will be equal to x squared dx. Okay, so if dv equal this, what does v equal to? Remember, you integrate, right?
X cubed over 3.
Yes, we got it. X cubed over 3. Okay, it can put plus a constant because for simplicity over here for integration by part, the constant doesn't matter. Yeah, right. So for integration by part here, the constant doesn't matter. So we'll just leave the constant out, or just think about the constant itself. Okay, all right. So that was the first method of attack right here. Okay. Now, if you have done this, then this integral is going to become, okay, remember, this is going to be, okay, so that's the first method, okay, all right, so by part first. Now, this one here, you use u-sub, okay, to let you to do that. Okay, how about number 9? What method? What's the first method of attack? Even though the x here is in the denominator, we can write this as x to the negative second power. So we can still consider this is in the form of x to some power times a transcendental function right here, right? That's a transcendental function, okay? So what's the method?
They're saying in the chat by parts.
by part. Okay, so by part. Okay, thank you. So what I'm going to let u to be in this case?
ln x plus 1.
Okay, so yes. So first one over here, it is log, right? So log function. So we're going to let u over here to be equal to this ln of x plus 1. So let u to be that. Okay, the remaining part will be dv, right? Okay, so we have u equal to ln of x plus 1. And then we have dv over here to be equal to 1 over x squared dx. Okay, now by doing this, du over here will be equal to 1 over x plus 1 dx. Okay, what will be v? What's antiderivative 1 over x squared? Anybody remember? It is, use the power rule. Okay, so it is negative 1 over x. Okay. So, all right. So I think you did a good job. Okay. So that's the end of this 7.5. See you guys.